In this last very short vodcast, we're going to consider the relationship between Ka and Kb, now that we understand what those are. And this is section 16.8 in your textbook. So as you can see, there's a list here of some acids with their conjugate bases. I'm not exactly sure why they included HNO3, nitric acid, or hydroxide, like sodium or potassium hydroxide, because those are respectively strong acids and strong bases, and they don't have a Ka or a Kb. But I hope you do notice that as you go down the column of the weak acids, we go from stronger hydrofluoric down to weaker hydrocarbonate. And as the strength of the weak acids gets weaker, the strength of their conjugate base should be getting greater. Now, it says down here that the relationship between Ka and Kb is very simple. When you multiply them, they should equal the ion product constant for water. The PowerPoint didn't do a very good job of explaining that. So what I've done is cut and pasted and scanned a picture out of your textbook from page 693, showing how this could be derived using a specific example. But if you know Ka, you can find Kb, because we all know the ion product constant for water is 1 times 10 to the negative 14. So here's that section from page 693 in the textbook, and it shows on the first equation NH4 ammonium donating a hydrogen ion, so it's acting as an acid here. And in the second equation, it shows ammonia, NH3, accepting a hydrogen from water, acting as a base. So each of those could have a Ka and a Kb expression written for them. So if you were to add equation 16.38 plus 16.39, as you see down at the bottom, you can see that the sum of those two equations is just water self-ionizing or undergoing auto-ionization. A more correct way maybe to recognize that would be two waters added together would yield hydronium, H3O, plus hydroxide, but the simplified version down here at the bottom is just fine. So as you know, when we sum two equations, if we know the equilibrium constant for each of those two equations, the summing of them to come up with a net equation, to find the KQ for the net equation, you just multiply them. So when two reactions are added to give a third, the equilibrium constant is found by just finding the product of the Kas and Kb for each of the two substituent reactions. So if you substitute in the value that we had a moment ago for the Ka of NH4 and the Kb for NH3, if you substitute those in, you would find that you simply have 1 times 10 to the negative 14 will equal the Ka times the Kb. So if the Ka gets small, the Kb gets larger and vice versa. And as we said at the beginning as we analyzed that table, the stronger that weak acid is, then the weaker its conjugate base is, and vice versa. And finally, you can also take pKa and pKb's, that is the negative log of the Ka plus the negative log of the Kb would equal the negative log of the Kw. So let's do a simple problem. It says calculate the the base dissociation constant for the fluoride ion and calculate the acid dissociation constant Ka for the ammonium ion. And a lot of times what happens in the table, they'll give you just the Ka and you have to find the Kb or vice versa. So when you go to the chart, you won't find fluoride, which is the conjugate base of hydrogen fluoride, and you won't find ammonium, the conjugate acid of ammonia. Let's make sure we have those straight. When you see ammonium, NH4+, that means that's what's left when an NH3 had accepted a hydrogen. And whenever you see an anion like fluoride, just put an H in front of it to identify what the acid would be. In this case, hydrofluoric acid. So I would say that if I go to Ka for the weak acid hydrofluoric and look it up, it's 6.8 times 10 to the negative 4. If Ka times Kb equals Kw, then Kb would be equal to the ion product constant for water divided by the Ka. So it's really simple math. I would do exactly the same thing for the Kb for NH3. They're asking me about the ammonium ion, but I only see the Kb for NH3. So we set it up this time, solve for the Ka. That should equal the ion product constant divided by the Kb. Very simple problems to do. And in a future problem, I will be giving you in the next chapter much more complex problems that include this step, using the Ka and K to find the Kb and vice versa by knowing 1 times 10 to the negative 14. We will start up next with a vodcast that shows how sometimes putting ionic substances into water can change pH. It's a fairly complex section, so I will stop this vodcast now.